in this video, we'll talk about how we'll use derivatives in programming. Okay, so let's look at that. So from our previous video, we have already created a function for that derivative, right? And look over here now. A derivative would look like this, right? Limit as h goes to 0, function of x plus h minus the function of x divided by h. Okay, so if you look at this function over here in my screen, then that function only incorporates this uh, part of the equation that we found, right? This part of the derivative function. We still have this part of the equation that we need to address over in the code side. Okay, so how do you address this? How? So if you think about this, our main idea of putting this term is that we wanted the h to be very close, like very small, so that the 2 points were very close, right? So that means our h should be a value that is nearly 0. Now what is a value that is nearly 0? So we can take a value, for example, h is 0.000001. Okay, so if you look at this value, then this value is very small, right? Very small. And so we can literally use this value instead of using this term. Okay, limit as h tends to 0. So limit as h tends to 0 literally means that your h is very small. So this is how you would write it down in code. Okay, so now let's calculate the derivatives. And just because we know what the derivative represents, we'll show we'll look at something magical that will happen. Okay, so let's say our x is a 1. So if my x is a 1, what would my derivative be? Derivative would be the derivative of x and for that h. Okay, so I'll get a derivative, and I also want to know my y value. So my y value is basically the function of x. Okay, that makes sense, right? So let me print my y value. Okay, so over here, let's actually compute that, and I get this. Okay, so let me look at that over here. So let me change the color. So you have your x value, your y value, and your derivative. If my x is 1, then my y is 1, and my derivative is 2.0. Okay, let's just truncate all of the part beyond these numbers that we have. Now here's something very amazing. So for this function, even if you don't know anything about the graph, you can just look at that number for the derivative, right? Which is 2. What does that represent? That means that if you increase your x value, then you are expecting an increase in your y value. Okay, does that make sense? That is what okay, so let me actually write that down. So derivative over here is a positive 2.0, right? That means that y and x are directly proportional. This means that if I increase my x value, I will see an increase in my y value. Does that make sense? Now let us suppose that what we want, okay, what we want, our result, we expected y value. Let's say we expect to make our y value 4. Okay, does that make sense? Okay, if we expect to make our y value as 4, okay, what would you want to do to your x just by looking at the derivative? Okay, so that derivative tells you that if your x value is increased, right, your y value should increase. Okay, so our expected y was a 4, right, and what we got was a 1. Okay, so how far away? Okay, how far away? So let me show that over here. This point, okay, so this blue point over here is our expected y. We want to make our y value 4. Okay, and over here is my actual y value that I got right now. If the value over here is a 1 and we wanted to get a 4, Does that make sense? And over here, the derivative we found was a 2. This means that if I increase my x value, right, I will reach, so this y value will also increase, and so it will reach that expected y value. Does that make sense? Okay. Now, what do we have to do? We have to increase our x. Okay, so let's increase our x. Let's make our x a little bit step to the right side, which is 1.5. Okay, so I increase my x by 1.5. So you can think of this in one dimensions like this. Okay, so I am at x, which is 1, and I want to increase my x, so I take a step over here, and this is let's say we increase the x to 1.5. Okay, so this is my new x. Okay, what does my derivative tell me? My derivative tells me that because I have increased my x, I should see an increase in my y value as well. Okay, so let's compute that. Okay, I computed, and my y value turns out to be 2.25. Okay, so let's, instead of looking at y in a horizontal way, I think it's better to look at it in a vertical way. So now, what is our expected y? Our expected y is a 4. What did we get? 2.25 is what we got, right, for our y value. What does the derivative tell you? The derivative at this point over here, right? So let me make it more explicit. At this point over here, my derivative is 3.0. So my derivative tells me that I should increase x some more, so that I will increase my y some more. Okay, and then I would reach that expected value. So if I want to reach that expected value, I want to increase my x some more. Okay, so let's increase our x some more, and let's make our x a 2.5. Okay, increase the x. Now I'm going a bit fast over here, so let us calculate my y value again. So what this is what I get for my y value. Okay, over here, so my y value is 6.25, and what is my derivative at that point? Derivative is 5.0. Okay, and what is my expected y value? Expected y value is still 4. Okay, now look at this over here. My y value is more than my expected y value, right? So what I want to do is I want to decrease my y so that I reach very, very near to my expected y. Okay, so I want to decrease my y value now. If I want to decrease my y value, then I look at the derivative. I see that if I take a step more in the x direction, I am gonna increase my y value. So if I want to decrease my y value, I should step down in my x value. Okay, so this would mean that I would want to go one step, like I want to step in the left side, so I need to decrease my x so that I can finally decrease my y value and almost reach my expected y value. Okay, so let's do that. So let's say I decrease my x from 2.5 to a 2. Okay, and then I calculate. Okay, and okay, just remember that this was when we took our x. So this whole thing came about when we took our x value to be what, 1.5. This thing came out when we took our x value to be a 1. Now that x value being a 1 was very random, right? And then over here we took our x value to be 2.5, right? And so we now need to decrease that. When we decrease that x value, then here is what we got. Our expected y value became our y value, which came out to be a 4. So this happened when our x value is 2. Okay, so now that x value of 2 is exactly what I want if I want my expected y to be a 4, right? So I am done over here. So I have reached the value that I wanted to reach, and I'm done. So I don't really care about that derivative anymore, because I don't want to move left or right. I'm exactly at that point. Okay, so this thing that we just did, okay, this exercise that we just did, this is literally how a neural network works. Okay, we have not built a neural network yet, but trust me, this is literally how a neural network would work. Okay, and this idea is actually the idea of gradient descent. Now we'll be talking about this more in depth, but just remember this idea. Okay, just by having that number, that derivative, I can now know if I want to step x in the positive direction or in the negative direction if I want to change my y value. Okay, and then whatever we expect, we can literally get that value out. Okay, cool. So now that we have this done, I was doing some of the stuff, if you remember, right? I was doing some of the stuff in repeat. That was I was increasing my values and decreasing my values based on my derivative. Okay, so let's change that a little bit so that we can automate that process. So let's see how the automation of that process would look like. So if I wanted to automate my process, then over here, 0.00001, right? The value for h didn't really change. Okay, my x value, in starting x value, was a random number, so I could use a random number, and or I could just assign it as a 1. Okay, some matter. Now what we want to do is, we of course need the expected y value every time we want to compute your y value. Okay, this is cool. Every time you would want to compute your derivative, that is also cool. This steps remains the same. Now over here we need to do some kind of a comparison. Do you remember what we were comparing? So my screen recording has stopped. Let me start that again. So the thing we were comparing was how much do I need to, like, we were comparing the y value and the expected y value. That's what we were doing. So let us do that again. Let's compare our y value and expected y value. Okay, so the way you would compare that, okay, so for example, in this case, when our expected y was a 4 and you got a 1 for your y value, then the way you compare it is you need to know how much more you need to go upwards or downwards. Okay, and the way you would do that would be you'd calculate the difference. Okay, so how different is the y value from our expected y value? So over here the difference would be 4 minus 1. Okay, that would be 3. That makes sense? Okay, so what I want to do is I want to minimize this difference. Okay, I want to minimize this difference, because if my difference is very, very small, then that would mean that my y value is very, very near the expected y value. Does that make sense? Okay, now let's look at another case that we had. So that is when we overshot. Okay, our y value became what, 6.25, and our expected y was a 4. Over here, what would be the difference? The difference over here is 6.25 minus 4, which is what now? 4, 5, 6, 2.5, 2.25, sorry. So that would be the difference, right? And we want to reduce this difference, because when that difference is very, very small, our y value is equal to our expected y value. So let's think of a formula that we can do this from. So over here, this 4 is actually the expected y. So it's too hard to write expected y all the time. So let me just write that as a y dash. Expected y is y dash now. So that means this difference, the way I calculated was y dash minus y. Okay, and this difference is y minus y dash. So we already have a conflicting term over here, because I'm calculating y dash minus y over in one side, right? and I'm calculating y minus y dash in the other side. So let's just make it so that our formula is consistent. So instead of saying y minus y dash, let us just make this as y dash minus y as well. Okay, so if you do that, then the computation will look like 4 minus 6.25, and this would be 2.25. Okay, so I get two numbers now, a negative number and a positive number, and I don't really care about this number being a negative or a positive. Okay, I just want to know if the distance between them is reduced. So again, the way you reduce that distance is to take that number to a 0. Okay, so the easiest way to do that would be add a square to the formula, and then all of your negative numbers will also become a positive number. Okay, so over here, that would then be y dash minus y whole squared. The same thing over here, y dash minus y whole squared. So when I would compute that, I would get 3 squared over here, which is 3 3s are 9. And this would also be negative 2.25 squared. That would be some number that I don't know. So I have my trusty calculator to do that computation. 2.25 into 2.25 would be 5.0625. Okay. So what I basically want to do is I want to reduce this. Okay. Now we are going to generalize. Remember, mathematicians love to generalize. Y dash minus y whole square. I want to take this term as close to 0 as I can. Okay, does that make sense? Okay, so let's do that now. Comparison. Comparison is my difference. So my difference is y dash minus y. Y dash was my expected y. So expected y minus y. And I would like to square these. Okay. I'd like to square that difference. And now over here, what I would want to do is make the difference 0. Okay. How would you make that difference 0? Now, that's another question we need to answer. So let's look at that. Let's look at how we did that before. Okay. So the way we did that over here was when my y value, or the difference over here, right? So let's talk about in terms of difference. So let me do it completely differently over here. This is my expected y. This is my y for 1 and 4. This is my expected y and y when we, this is expected y. This is y when it was 6.25 and a 4. Okay. So over here, in this case, what was my difference? Okay, and the difference over here was my diff. What did we calculate? That was 9. Okay, what was my difference over here? It was 5.0625. okay. So over here, if I want to minimize my difference, right, then when my y dash value, so this case is basically y dash being greater than y. You'd agree? And this case would be my y dash being smaller than y. Okay. So when your y dash is is greater than y, then you are interested in increasing your y value. So that would mean that you are interested in increasing your x value so that you get there. Okay. And if your y dash value is smaller than your y, then you're interested in reducing your y value so that your y is near y dash. Does that make sense? So over here, I am interested in increasing my y value so that my y is almost equal to y dash. I am interested in decreasing my y value so that I am almost like near to that expected value. So what do we want over here? If your difference is a 0, okay, if your difference is a 0, you have basically got your answer. Okay, so your answer would then be your x value. So whatever your x value you're at, is the x value you want, so that your y value is your expected y value. Okay. If that is not the case, then you would want to adjust your x value so that your y values get adjusted, and then it's nearly equal to expected y. The way that is done is if, okay, if your expected y minus your y value is a positive number. So what you want is, if your expected y value is greater than, okay, I think I can do it this way. If it is greater than your y value, right, then what that means is you basically want to, you basically in this case, so you'd want to increase your y value, which means you want to increase your x value. So let's increase our x value. So x value, let us say, is increased by by some amount. Okay, let's say 0.5. Okay, so because we're increasing our x by 0.5, right, 0.5 is the step size. Okay, so let me extract that variable as step size. Step size is 0.5, sorry, 0.5, not 0.005. Okay, and this would be increased by a step size. Okay, if it is the case that your y value, or let's say expected y value, is less than your y value, then that would mean that you would want to decrease your x value so that your y, so it's this case, right, your y value, you want to decrease it so that it's near the expected y. So negative step size. Okay, and you want to do this all the time until your difference is a 0. Okay, so let's do this whole thing, and you'd want to compute your y again, you'd want to compute your derivatives again. So let's do it in a loop. So while 1, okay, and then you do all of this, and I just realized that this is not how you do Python. Yeah, so let me fix that. Okay, so this is our loop now. Okay, first what we do, first thing is we need to initialize your x value to a random number, let's say 1 in this case. And then what you'd want to do is, every single time you'd want to calculate the y value and the derivative, find the difference, and see that if that difference is a 0, then you print x. And if you already find a difference to be a 0, then you're done, right? So you need to break out of the loop, don't do anything below that. You don't need to do it anymore. You don't need to adjust your x or y. If that is not the case, then adjust your x or in the positive or negative direction, depending upon the derivative. Okay, oh wait, we should also incorporate derivative over here. So if your expected y is greater than your y, and you need to see what's happening to your derivative. Okay, that's my bad. Okay, look, in this case over here, if your derivative is a positive number, okay, if your derivative is a positive number, then you would want to increase your x value. Okay, because x and y would be directly proportional, so you'd want to increase your x value. So this would be increase. If your derivative is a negative number, okay, if your derivative is a negative number, you would want to decrease. Okay, so because decreasing x would mean that your y would increase, right? Negative just means directly proportional. If your derivative happens to be a 0, and your y dash is still like less than your y, then you're interested in increasing. So it does not matter what you do, you can increase or decrease. So over here in this case, it's gonna be exactly opposite, right? Oopsie, gotta paste that. Yep, paste. So in this other case, then you would want, so if your derivative is positive in this case, okay, in this case, then that would mean that increasing x will increase y. You don't want to increase y, you want to decrease it, because your y is already greater than y dash. So you would want to decrease, and over here you'd want to increase, and over here you can do anything, doesn't matter. Does that make sense? Okay. So let's generalize this now. Okay, so the way you can do it over here is, over here you still have two cases. Okay, if your derivative is it positive, greater than 0, if you are greater than 0, what should you do? If you are less than 0, then it does not really matter, right? You can do anything. So you'd want to, if you are greater than 0, then you'd want to increase. If you are less than 0, let's say you'd want to decrease the step size. Okay, makes sense. Over here it's the same kind of concept. D is greater than 0 would mean that you'd want to decrease, right? Yeah, it's positive, you decrease. If it is negative, you would want to increase. Okay, does that make sense? Okay, cool. So this should do, okay, this should do in theory. So let's run this and see what we get. Okay, we start your x with a 1, we have this step size, we expect our y to be a 4, so let's get our answer. And the answer that we get for our x, okay, is a 2. This means that when your x is 2, you are expecting your y to be a 4. So good. That is very good. Okay, so this thing that we just did over here, okay, this whole thing, this is a phase for training neural net. I know that I have not introduced neural net yet, but this is how you would actually train neural nets, okay, using that derivative. Just because we have that derivative that can tweak, that can tell you that if you tweak your x left or right, what is going to happen to your y. You have this way of you have an algorithm now that you can tweak your x's so that you would get your expected y value.